Greetings, welcome to another great video. So here we have a past paper problem. So the main focus for today's video is on electric circuits. So this is just a past paper problem on electric circuits. Gert Sibande from April 2023, right? Now we have, this was a question 3 on this topic test. So we are given a circuit and it shows that there's an 8-volt battery with negligible internal resistance, right? So since they're saying the internal resistance of this circuit is negligible, it means you have R, your small r, it will be equals to naught, right? You just assume that it's naught. So it means now the EMF, which is 8 volts, is also the total voltage supply of the circuit. Remember, if the internal resistance was not negligible, it means we would have to find, usually they would give us an EMF, and then we would have to find the actual voltage that is being supplied in the circuit, because usually the EMF is not what the circuit will use, because some of the voltage, if there's internal resistance, some of the EMF is consumed while overcoming that internal resistance. So you end up having the circuit being supplied a voltage that is lesser than the EMF. So in this case, the 8 volt is the total voltage for the whole circuit, okay? The total potential difference for the whole circuit. Now, you have we neglect the internal resistance and also the resistance of the conducting wires themselves. And then when switch S is closed, so they close this at some point, the reading on the ammeter, which is ammeter A, is 2.2 amps, okay, while the reading on voltmeter V2 is 4.4 volts. Okay, so all these values are given in the circuit, so you don't really need to write them down or anything. By just looking at the circuit, you can see all these values are here. Right, now what I always say is always start by tracing your current. Check where it's going, where it branches off, where, and so on and so forth. Then you would understand your circuit better. Before starting to answer any question, check where or how the current moves or circulates around the electric circuit. So let's start. We know that it'll exit from the longer side of these lines that represent the cell or battery. So it'll exit this side, right? Or it'll move that side. Then you have, initially you'll have the total current, so it moves. This is still the total current. It goes all the way there, and then it gets here. When it gets to this junction, if you may, it divides. The first branch will get, we can name it I1, which means the current that will flow through the first branch of the parallel combination, because these two resistors are connected in parallel, right? And then the second branch will get I2, which means the current that will pass through the second branch. Okay, so that's what we have there. We have I1 and I2, okay? And then, so the 3 ohm resistor will receive I1, while the R ohm, because we don't know what the magnitude of that resistance is, the R ohm resistor will receive I2. Okay, then at some point, they coincide here again, these two currents, then they combine again to form the total current. All right, so then we get to the 2 ohm. Be careful now, this is not a resistor, it's just a voltmeter, so the current here won't divide. Even if it did divide, it cannot flow through the voltmeter. Current can't flow through a voltmeter. Remember, the reason for that is because a voltmeter has a very high resistance. It's too high. So current usually, it sort of runs away. It doesn't like too much resistance, so it wants to flow in the direction or in the path of least resistance. So that's why whenever we connect a voltmeter, we connect it in parallel to that resistor whose potential difference we want to measure, right? So there's nothing that will flow to that voltmeter. So this is just total current flowing through the 2 ohm resistor. Then it flows, it goes all the way there, and then it recirculates again. So what that means is the 2 ohm resistor will get the 2.2 amps. All right, because that's the total current that is measured by that ammeter. The ammeter measures the total current. We have established that by now. As you can see, when we trace the current, we see that the ammeter will measure the total current of the circuit. Right, then V2 also gets 4.4 volts. All right, so now what happens here is we are done tracing the current. Now another thing we can do is interpret the circuit. Okay, so if V2 is 4.4 volts and my total voltage supply for the circuit is 8 volts, it would mean that the remaining, it should be 8 minus 4.4. That's something like 3.6. Right, so 8 minus 4.4, yes, 3.6. So the remaining 3.6 volts goes to V1. Right, if you think about it, the remaining 3.6 volts goes to V1. So V1 will measure the voltage of the parallel combination. So what that means is the 3 ohm resistor will get 3.6 volts, and then the R ohm resistor will also get 3.6 volts. Now why does that make sense? Because in a parallel circuit, if you remember, you always get the voltage being the same across the resistors. So even if we had about 4 or 5 resistors and so on, the potential difference will be the same for the entire parallel combination. So each resistor will receive 3.6 volts. So the only thing that divides is the current. So always remember those simple rules, okay? So this is how you interpret any question. Before you start answering, you check the diagram, you make those small calculations like what we did here. We knew that this is 4.4 volts, and then if that's 4.4 volts and we have a total of 8, it means V1 has to take the remaining, which is 3.6 volts. And if V1 is 3.6 volts, it means the 3 ohm resistor gets 3.6 volts, and the R ohm resistor will also get 3.6 volts. You can even write it here if you want, 3.6, and then this one will also get 3.6 volts. Right, so you see, we haven't even started answering the questions, but already we know what's going on in the circuits. We know everything about the circuits. All right, so let's start with, I think we can go ahead and start answering the questions now. So we have 3.1, that is Ohm's law. That's that, Ohm's law. We are required to state Ohm's law in words. Right, so if you remember, Ohm's law is basically saying that the potential difference is just directly proportional to the current, right? Obviously, provided that the temperature of the conductor remains constant, right? So that's the condition. Otherwise, if it doesn't remain constant, then this law won't hold. It becomes the relation between these two parameters sort of changes, right? So yeah, that's basically Ohm's law. You have to know all these definitions before your major test or exam. It's 3 marks, honestly. This should have been what, your free 2 marks, right? Out of 18, you already have 2 marks. So Ohm's law, you would say Ohm's law states that the potential difference across a conductor is directly proportional to the current flowing through it, provided that the temperature of the conductor remains constant. Okay, that's it. So unlike the other laws, here you don't have to say inversely proportional to this, but directly proportional to that. It's just directly proportional only. Yes, so that's it. Let's write Ohm's law. So yeah, the potential difference across a conductor is directly proportional to the current flowing through it, provided that the temperature of the conductor does not change, so it remains constant, right? So that's how you would state Ohm's law. Obviously, some people would say the potential difference across a conductor is directly proportional to the current flowing through it at constant temperature. It's still fine, really, it's acceptable. So let's go to 3.2.1. Now we are required to find the reading on voltmeter V1. Okay. Reading on V1. All right, let's go check V1. Oh, it's 2 marks. So we've already done it when we were sort of analyzing the circuit itself. So V1 is simply equals to 8 volts minus 4.4, which would be 3.6 volts. This is how you would have done it. Or if you want to make it look like you are, if you want to take it step by step, you would say, so the V total, right, is V1 plus V2, because clearly V1 measures the parallel combination and then V2 measures the series connection. So we know that if we add those two, we would get our total voltage, but we already know the total. We say that's 8 is equals to V1 is what we're looking for, plus 4.4. And then you transpose and then you say, well, V1 is 8 minus 4.4, which is essentially 3.6 volts. But for 2 marks, this is just fine. But if you want to take it step by step, you can write it the other way around. Still fine. All right, so this was a straightforward question. Let's go to 3.2.1. Okay. What is the value of the resistor R? Okay. So for resistor R, we know the voltage, right? But we do not know the current. So we can't straight away, we can't just say R is V over I. So we have to figure out how to get there. Okay. So here you would have pretty much two options. Both of them would require you to use mathematics, right? So let's check it out, right? If you remember, we have the total current. We have the total current being 2.2 amps, right? This is our total current. Right? So we know that if we have the total current, remember what we're trying to find is R, and we're trying to relate how the total current is distributed between these two resistors. We can always use the ratio method, right, for a parallel combination. That's method 1. Method 2, what we can do is we can say, well, let's find the total resistance of these circuits and divide it by, we know if we say R is V over I, we already have the total voltage and the total current. So from there, we would be able to solve for R. So let's divide it. Let's start with method 1 actually. Method 1. So I'll just show you two methods to show you that you don't have to limit your thinking when it comes to these things. There are usually a number of ways into which you can attack a question and try to solve for it. So method 1, using, I'll say we are using total resistance. or if total effective resistance, right? So what's our total resistance? Total resistance, we can say that R tot, let's call it R tot, is equals to the parallel combination plus the series combination, right? Now what's the parallel combination? Since there are two resistors in parallel, we can simply say R1 times R2 over R1 plus R2. Now this formula is for the parallel combination, right? And for the series guy, we can just say, well, it's R series, right? Now let's sub in values. So the parallel resistors I have, let's show you. Let me show you. I have the 3 ohm connected to the R ohm. That's my parallel combination or parallel connection. Then I have this 2 ohm resistor connected in series with the parallel combination. Okay, so that means what I can do, I'll say my R1 is that 3 ohm times R. That's my R2. Then this is 3 again plus R. Okay, then plus. Now here I will add my 2 ohms, which is the one that's connected in series with this to this parallel combination, right? So if you add here and you use your maths, you will notice that you should have 3R plus 2 times 3 plus R. I will stretch it a bit, but I could have just easily written the final expression, but it's fine. And then this is 3, common denominator, remember? So that's maths. It's maths at this point. It's not physics. It's just maths. So now this means you would get 3 plus 2R, that's 5R, plus 6, all this divided by 3 plus R. Now this is an expression. This is an expression for the total resistance. Okay, that's my R tot. That tot means total resistance. I don't want to write it like this. Total. I want to write total. I don't want that. So I write tot. Tot sounds cooler, if you know what I mean. So R tot is equals to 5R plus 6 over 3 plus R. Okay, now so what I can do now is I know my V tot. Remember, my V tot is 8 volts, whereas my I tot, which is my total current, is 2.2 amps. So what does this mean for me? It means that I can say R tot using Ohm's law is equals to V total over I total. Right, if you check from here, I would be able to solve for my R, because on the right hand side this would give me a value, and then I would be able to solve for R. Let me show you how it looks like. So let's take this. All right, so we are saying, if I say R tot, I can easily say this is equals to V tot over my total current, total voltage over total current. Then we know that this is 5R plus 6 over 3 plus R. Okay, and then it's equals to 8, which is my total voltage, remember, divided by my total current, which was 2.2. From here I can solve. Okay, so it's up to you. It's either you cross multiply from here, right, like this, or you simply simplify the right hand side into one digit and then you solve like that. It's up to you. So in my case, I'll choose to cross multiply. It doesn't matter. You can do it either in either way. You'll get the same answer. So if I cross multiply, 5 times 2.2 should be 11, right? 11R. 6 times 2.2 should be, what is that? 6 times 2.2, 13.2. Okay, 13.2 equals 8 times 3 is 24. 8 times R is simply 8R. From here, you can group things. You can have 11. This is just maths at this point. If you don't know what I'm doing here, it's a mathematical operation. It has nothing to do with physics at this point, okay? You have to revise your maths, right? So I'm just grouping now. I transposed 13.2 to the right-hand side of the equation, and then I transposed 8R to the left-hand side of the equation. I could have done it the opposite side. It doesn't matter. You do what is simpler to you, okay? So now you have 3R is 24 minus 13.2 should be 10.8. From here, you divide both sides by 3. I'm taking you step by step, right? And then that means your R would be divided by 3.6 ohms. Okay, so you see, so we did the exact same thing you would do if R was a given figure, right? In an event where you were required to find either voltage or current, you were going to say R is V over I, and so for whatever you need. So the only trick here was understanding that it doesn't change the approach, even though now R is in a form of an expression or an equation. It doesn't mean it's something different. You can still solve for it the way we usually solve for these problems anyway, right? All you had to do was understand that. So with method 2 using ratio method, remember that method, right? Method 2, let's call it method 2. If you remember, with the ratio method, what we say is the ratio of my current that's in the first branch to my current in the second branch is the ratio of my resistance in the second branch to my resistance in the first branch. So if I substitute here, right, it means I1 is to I2, right, would be, what is my R2? My R2 is simply R. We don't know what that is. What is my my R1? We said R1, we will take it as 3 ohms. So remember, come here again. This is R1, corresponds to I1, right? And this is R2, corresponding to I2, okay? R1, R2, that's it. So the ratio method says we can do it like that. You flip these things. You see, you don't say, it's incorrect to say, let me do it here. I1 is to I2. You must say R2 is to R1. So what we're saying is the ratio of my current 1 in the first branch to my current in the second branch is the same as taking the ratio of my resistance in the second branch to my resistance in the first branch. The reason we swap the resistances is because what happens in a parallel circuit combination, if you remember correctly, the branch that has the highest resistance will get the least current, and the branch that has the lowest resistance will get the most current between the two. So that's why you flip it, right? So that law is not violated. Because if now you say I1 is to I2 and then you have R1 is to R2, then it won't hold. That rule I just set out won't hold. So what you would be saying here is the one that has the highest current will receive the the one that has the highest resistance will receive the highest current, and the one that has the lowest resistance will receive the lowest current, which is not true. Okay, so it's opposite, right? That's why whenever we take the ratios, we flip the resistors, right? So in essence, what I'm saying is this is the correct way of doing it, right? That's the correct way of doing it. And then this is the incorrect way of doing it. So take note, have a mental note. Okay, so from here, remember what the ratio method says. It says, now depending on whether you are looking for I1 or I2, so in this case we are looking to solve for R, so we'll assume we are looking for I1. Okay, so how you do it is you would say I1, right, is equals to you first add your ratio. So if these were numbers, let's say R was 1, when you add, you would get a 4 here. So that would be your denominator. So you would say over R plus 3. In this case, R is not a value, so we'll just leave it as R. So that's our denominator. Then what's our numerator? Our numerator is the side we are focusing on, the one that we want. So that's our R. Right. Then we multiply this, by our total current, I tot. So what this expression or this equation is saying is that now I1 is a fraction of the total current. So I want to understand that how much of the total current will be I1. So for me to get that, I need to understand that out of the total ratio of I tot, a certain percentage will go to I1. So how do I represent that? I use this. So that's all it means. So it's more of a mathematical expression than it is physics, right? So that's all it's saying. It's saying I have a total. If you think of it in terms of fractions, it's saying I have 100%, right? And if I get, let's say out of 100, I get 30, how much of the, how much of the actual amount will I get? How much of the actual share will I have? So here you would put the quantity. It could be 50, it could be whatever. I'm just making an example. So what's the percentage, or what's the fraction of the total current will go to I1? How much of the total current will be distributed to I1, and how much of the total current will be distributed to I2? So if I wanted I2, I would say I2 is equals to, I go to I2, that's my numerator, 3. My denominator is always the same, which is the sum of the ratio. That would be R plus 3 times now my total current. Right, that's how you would find it. Right, so for current, this is how you do it. For voltage, you don't flip it, because voltage is the same, right? So you would use the ratio method for voltages for a series connection. In a series connection, you don't flip it. You would say V1 is to V2, should be R1 is to R2. But you do that for a series circuit, not for a parallel. In a parallel circuit, remember, voltage does not divide, it stays the same. Right, so you will use this to understand just how much, or how does the parameter we are concerned with, how does it divide, and how is it distributed to each resistor. So if you check from here, we can then solve using this guy, right? Okay, so what is I1? Let's go there. I1 is the current in the first branch. Do we know I1? No, but we can find I1. Why? Because we know the voltage in that branch, we know the resistance in that branch. The voltage is 3.6 volts. And what about the current? It is, no, not the current, the resistance. The resistance is 3 ohms. So we know that I1 has to be R1 over, V1 over R1, right? That's all. So you can come here and do it. This is V1 over R1. Let's continue. We have R over R plus 3. I'll substitute once I'm done expressing it. That's the I taught, right? So now we can substitute. What's our V1? We said is 3.6. What's our R1? We said is 3. Here we don't know. We are trying to solve for R. Then it's R plus 3. What's our I taught? It's simply 2.2, right? Now we can cross multiply. This is gonna be 3.6 times R plus 3 is equals to 3 times R times 2.2, right? That's what we have now. So we can solve here. If you think about it, we can now solve. So to make your life easy, what you can do, you can divide both sides by 3.6. 3.6. So what you'll have here is R plus 3 is equals to, let's punch this in a calculator, 3 times 2.2 divided by 3.6. Actually, to avoid this whole headache, sorry, let's do this. We can just simplify it from here. 1.2 is equals to 2.2 times R over R plus 3. Yes, much better. Right, from here you can solve, right? You know that this is over 1, then you can cross multiply. Now it's much easier. So you'll have 1.2 R plus 3.2, because 1.2 times 3 should be 3.6, or 3.6. And then here you'll be left with that 2.2 R, right? Then from here, if you transpose the R, you'll be left with R is equals to 3.6 ohms. This is the same answer as before, right? So yes, it's either you use the ratio method or you use the total resistance method, whichever way you would have thought of first, or whichever way is quicker for you. It works nonetheless. All right, so let's go to 3.2.3. Now, the energy dissipated in the 2 ohm resistor within 5 seconds. All right, so we know, remember, energy, this, what number is this? 3.2.3. okay, yes, 3.2.3. So remember, energy is power multiplied by delta T, time. Now, depending on what you're looking for, you can either report energy in joules or in kilowatt hours. But in this case, we are not trying to calculate the electrical, the cost of using this bulb, right? Is it a bulb? But we're not trying to calculate the cost of using this resistor. It's just a resistor. So what we'll do is we will leave it in joules. So when you want to calculate energy in joules, you use time in seconds. So if the time was given maybe in minutes, or if the time was given in hours or days or whatever, you would have to convert it to seconds and then calculate the energy. But in this case, it's already given in seconds, so we can just find energy. So we already know the resistance and the time, right? So what else do we know about the 2 ohm resistor? Because we can't use those two only to find the energy. So the 2 ohm resistor receives 2.2 amps, okay, and it also has 4.4 volts, okay, right. So what we have to do now is we think power can either be calculated as V squared over R, or it can be calculated as P is I squared times R, or it can be calculated as P is simply V times I. Yes. So you check which one works best, or which one, in this case, we can use whichever one in this case really, because you have voltage, you have current, you have resistance, you have all of them, right, for the 2 ohm resistor at least. So I'll choose the last one. So I can say energy will be voltage times my current times my delta T, right? So if you check this, it's similar to that formula work, is voltage times I times delta T. It's similar, right? So yes, you can do it like that. You can use any of these formulae actually. Now let's find it. I have 4.4 here. I know my current is 2.2. I've been told that it's for 5 seconds. So now I can find it. 4.4 times 2.2 times 5. I get 48.4 joules of energy in 5 seconds. So this is how much energy that the resistor will dissipate within 5 seconds. So this one, it's quite, we didn't have to choose a formula. You could have used any of these ones. So in this case, you can use any of this. Any of these, they work. Right. So you can, for your own exercise, you can pick V squared over R and I squared over R and see if you'll get the same answer as I did, okay? Now for 3.2.4, the power delivered by the 3 ohm resistor. Which one is that one? No, that's R1. Okay. This test was friendly to the learners. Or this question rather, because I don't know. Maybe the other ones. Alright, so power in the 3 ohm resistor, we know our voltage. So we can say V squared over R, because we don't know the current. So I can't use V times I or I squared times R, because I don't know the current. I can calculate the current, but it'll take me an extra step. I don't need to. So this one is just plug and play. I can use this one, okay? So my voltage is 3.6. I square that. My resistance is 3, because it's a 3 ohm resistor. So what power do I get? They only wanted power, right? Let's see. Power delivered by the 3 ohm resistor. Yes, just power. So if that's the case, we get 3.6 squared divided by 3. The power there is 4.32 watts. Okay, so that's the power delivered by the 3 ohm resistor. So another one, this question was not that tricky. You just need to know how to use your formula. And then we go to 3.3. Give a reason why the voltmeters V1 and V2 are connected in parallel as shown in the diagram above. Remember what we said when we were still analyzing the question. We said the reason a voltmeter is connected in parallel to a resistor is because it has a high voltage. It has an extremely, not high voltage, sorry. It has an extremely high resistance, right? So the resistance is so high that if this thing was connected parallel to the resistor itself, it wouldn't be able to effectively measure, right? Because the current would avoid flowing through there, because current wants to flow in the path of the least resistance, right? So we usually connect voltmeters in parallel to a resistor whose potential difference we want to measure. So that's why, because it measures the potential difference and it has a high resistance. So unlike an ammeter, a voltmeter has to measure between 2 points like this. So it measures here and there. So the difference in potential, in electric potential. So it has to be connected like that. If it was just connected in series, it would not be able to do this effectively, because the current wouldn't flow there. It would be an issue. All right, so that's one of the reasons. It's usually the main reason, actually. So if I were to write that reason in short, I would say, so voltmeters are connected in parallel, right? Because they are designed to have an extremely high internal resistance, okay? So let's write that, voltmeters. So yes, voltmeters are connected in parallel because they have an extremely high internal resistance. So since it's 1 mark, I think you can leave it here. But if you were to further elaborate, you would say, well, connecting them in parallel allows them to measure the potential difference across a component without drawing any significant current away from the circuit branch, right? And then it therefore keeps the whole circuit current, or the total current of the circuit, it keeps it unchanged. Because remember, in a circuit, once you increase the resistance, the current is affected, or once you increase or decrease the resistance, the current is affected. So imagine if we connect a voltmeter in series. Already the voltmeter has an extremely high internal resistance, so it would affect the current in the circuit. So to avoid all of that, we usually connect these in parallel. Okay, so that's one reason. Now let's go to 3.4. Will the ammeter reading increase, decrease, or remain the same if the 3 ohm resistor is removed from the circuits? All right. So if we remove the 3 ohm resistor from the circuit, it means we will no longer have a parallel circuit combination, or a parallel combination, right? So the whole circuit will be in series. So what will happen if the whole circuit is in series? It means our new R tot will simply be R1 plus R2, which will be 5 ohms, right? Whereas previously our R tot, let's check previously, let's try to substitute here. Previously our R tot would have been 5. We said the calculated R was 3.6, right? Okay, let's try and see how much our, before we remove the 3 ohm resistor. So this is 5 times 3.6 plus 6, 3 plus 3.6. Cool. So before we remove the 3 ohm resistor, our total resistance for the circuit will be 3.64 ohms. Okay, this is the initial one before we remove the internal the 3 ohm resistor. Okay, now once we remove the 3 ohm resistor, our new total becomes 5 ohms. So you see the total increased, right? Okay, that's the first thing we have to note. So what happens if you increase the total resistance of a circuit? What happens? If you increase the total resistance of a circuit, the current will be affected. In what way? Since current is inversely proportional to resistance, the current will have to decrease because the resistance has increased. Remember, inversely proportional means as the other one increases, the other one has to decrease, or as the other one decreases, the other one has to increase, right? So that's what would happen. So the reading on the ammeter would therefore decrease. That's what we will say. So in short, let's write it here. They didn't want you to calculate anything, so you don't have to put values. I put values for you so that you can see the effect of removing that resistor, so that you can conceptualize it. So you would say decreases. Why? Because if we removing the 3 ohm resistor increases the total resistance of the circuit. So that's it. We're saying because removing the 3 ohm resistor will result in an increase in total resistance, since the current is inversely proportional to the resistance. So the total current will therefore decrease as a result of an increase in the total resistance, right? So yeah, that's it. That's how you would answer such a question. So that's it for this video. I will catch you on the next one. All right, cheers.